So basically, I'm going to follow the workshop page that can be started from the main site, PAW site page, and basically following this page that has already been written. And the point also was for you to possibly install a Rack and a Rack VCV SDK, and even possibly the VCV prototype, which is a module that you can program, and we have developed a Faust version for this VCV prototype. So assuming you have installed part of this, or maybe everything, you can try to do it yourself, what I'm going to present, otherwise you can just follow the workshop. So since we already had this nice presentation of VCV Rack by Max this morning, I'm not going to explain the software anymore, and you understand. So that it's VCV Rack, it's a software emulation of modular synthesis module that you can connect quite freely. The interesting point is that it tries to mimic what you can do with hardware module by connecting CV, control, and audio, and mix everything. And in some sense, you can blur the usual distinction between audio signal and control signal that we have in audio software. We usually speak about control rate and audio rate. And in this kind of approach, you can basically blur the two kind of signal, which is quite interesting because you can have more flexibility in the way you describe your patch. When you are a programmer, you have to know some more precise stuff, because since this software emulation is basically an emulation of the voltage approach, you have to know that signals are going to vary in a specific range, like -5 and +5 volt, or 0, 10 volts. And MIDI signals usually follow this 1 volt per octave convention. And this has to be known when you start to program with VCV Rack, because obviously you have to understand how the signals are going to be transmitted between modules. The other important thing to know is that obviously you can describe a monophonic module here, but you can also have a notion of polyphony. So some modules can transport polyphonic signals up to 16 channels, and on the user interface of VCV Rack, you will see that you have a thicker cable that basically says that more signals than only one is transmitted by the given cable. And in this workshop, I'm going to show 3 different things. First, we are going to behave as a regular C++ programmer that would have to use C++ from scratch to describe, to program a VCV module and to compile it and to install it into the software. The point of this is to give you an idea of what is supposed to be done usually when you want to develop a VCV module. And then obviously, we will explain how you can simplify all this process by using, in this case, the Faust language to describe your DSP. There is the VCV Rack developer give you an SDK that you have to install and configure a bit. And then they give you some helper tools that you can use to create a kind of template, module template that you will be able to update and modify so that you implement a real DSP and the GUI that you also want to use to control your DSP. So I'm going to execute part of the tutorial, you can look at the tutorial which is on the VCV Rack site here. I'm basically simplifying a bit the procedure. So here you have a first command that you can do. I'm going to switch into another screen. Here I am into my VCV Rack SDK. I can create my module and just use some default. And then at the end, what is created here is a new folder with some C++ code and a make file that you can use to compile. Sorry, obviously you have to go inside the created folder and you have to make it to compile it. Now, an interesting point of this VCV Rack module is the fact that you can, as a programmer, you can describe the GUI using a completely SVG-based approach. So basically, you can use a standard graphical software like Inkscape to describe the GUI, and they have a kind of convention so that you can decide to have you will have audio input, audio output, control voltage input and output, and knobs, parameter, and switch, things like that. And you have a color by using the specific color, you can describe to the system that you are going to need this number of input, output, control voltage, and knob, and so on. And then they have a Python script. They will analyze this SVG file and basically create some C++ code for you to help you create the user interface. So we are going to do that. I have already taken this SVG file. I have it, it's not done by default, but I have basically to copy it into the res folder of my plugin. And my plugin is basically the template folder I just created before. Then I go back and I use another command that will now analyze this SVG file to create some additional C++ file. And you see here there is a new file that has been created automatically. And this file basically contains code which has been created automatically and that will create the user interface. And you see that this module defines a process function that is going to be called to produce the actual sample. Yes, I understand I forgot to say something. The important thing also about VCV Rack is that since you have this blur between audio and control, it means audio is computed sample by sample. So basically you have a buffer of only one sample. So it means the process function that we just saw is going to be called sample by sample. Now, if I want to put some real code, I'm going to copy paste this code, which basically is going to compute a sinus using a phasor signal, which is fed into a sinus function. I just copy this code. I have to uncomment some code into the template file. I don't know why it's not done by default, but it's done like that. You have to uncomment this. And then you go back into the folder you type make, and then you type make install. And when you type make install, the compile plugin, which is in this case, yes, It's a dynamic library on macOS, and everything will be transmitted on, will be installed into your VCV application. And you can now start VCV Rack, and if everything works, then yes, you see here a new module. The module we just developed with C++, and that is supposed to output a sinus, and since I've not even tried to use the button is not even connected, just the sinus given fixed frequency. So, as you see, this is a way to describe, to program your own module. Obviously, to do something more interesting, you have to take a bit of time to implement more complex DSP into the process function, and obviously you may want to describe a more complex GUI. Again, you can use this Inkscape-based approach to describe the background and just add some button on top of the SVG background, or you can, if you want to, obviously in this kind of tool, you can do it completely by program. You can completely design your user interface by using C++ code. And this is something obviously we will have to do ourselves when we go to the Faust-based approach. Still okay for you? Yes? Yes? No feedback? Everything is working? Yeah, okay. So next step is now to show you what we have done to add Faust development capabilities into VCV. So there is basically two ways to do that. One is by extending the VCV prototype module, which is a project that is also developed by Andrew Beltz, same guy who has developed the VCV Rack application. And basically this project, which is on GitHub, gives you the capability to have a kind of template module with a fixed GUI with 6 input, 6 output, which can be either audio input, output, or CV input, output, 6 knobs, 6 lights, 6 switches that you can, which color you can control. And this VCV prototype can be programmed using either JavaScript, Lua, Volt, which is a domain-specific language, similar to Faust in some sense, or pure data. And obviously, what we have done here is adding Faust as a language that can be used into this VCV prototype along the other language that you can use at the same time, not exactly at the same time, but in the same session, you can possibly switch between JavaScript, Volt, Lua, and Faust. And as I explained just before, the user interface of this module is defined by advanced. You cannot change it. You can only decide how you are going to use the switch, the knob, the input, audio input, output from 1 to 6, and how you are going to connect basically your DSP code to this user interface. To have Faust running into this VCV module, we use libFaust, which is basically the library version of the Faust compiler. And libFaust can be used either with LLVM, JIT, or just-in-time compiler, so basically which allows to dynamically compile a DSP Faust program on the fly and execute them in memory directly. But since deploying LLVM, it's always a bit of pain because you have to download a huge project and compile it. For this specific example, we decided to use another backend, which is a part of the Faust compilation chain, which is a pure interpreter. that interprets some kind of bytecode that has been produced during the compilation step. And obviously that will run slower compared to LLVM, but it's fast enough to be used to prototype DSP code into this module. If you want to try it, since this Faust development is not yet part of the official VCV prototype module, you have to use a Faust branch on this project, and basically the Faust branch, you have a Faust implementation here, and you have additional documentation that right now is in a separate file that explain how you are going to use Faust into this context, and we are going basically to use to follow part of this documentation. Yes, sorry, I switched from window to window. So as I explained just before, since you have this fixed GUI, it means you have to, as a programmer, you have to decide how will you connect and which switch or knobs or audio input you are going to connect to your DSP. And the way we do that in Faust is using metadata. It has also been demonstrated this morning with the gramophone project. Romain just demonstrate how you can use a switch or knob metadata to connect a given parameter into your Faust code into a given hardware button on the gramophone, and in this case it will be connected to a graphical element into the user interface. So basically you can use switch from 1 to 6 to decide to connect a given parameter to a switch, which will correspond to a button or checkbox into Faust user interface element. You can use knobs from 1 to 6, and you can use this lighting system, which have each 3 blue color components, red, green, blue, and by combining them, you can basically light with any color the elements that can be controlled with this coloring scheme, basically. And basically you use it with output controller in the Faust terminology, and output controller are basically a bar graph. So this is an example of a button that you would describe in Faust syntax that would be connected to the switch number 1, and that will also be highlighted in red when you just hit the button, because well, basically the signal of the button is going through a bar graph, which is going to highlight in red. And here a bit more complex example of where you can even connect to 3 different colors at the same time. We are going to look at some example. Here I have to cut and paste this code into the VCV prototype. How do I do that? I just copy here. I have the VCV prototype with Faust support here. Probably I have to load I create a new DSP file. By default, this DSP file contains some default code. I'm just going to replace the default code with my code. And as soon as I save the file, it will be recompiled on the fly with the libFaust and the interpreter backend. And it's supposed to produce something. So I have to connect the output of this. So now we are, yeah, so it's working. So now we are trying to understand what this code is actually doing. So this code is basically outputting two different signals. This is the left signal, the right signal. The left signal is produced by an oscillator controlled by the frequency with a gain control. And here, as explained at the beginning, since we have to deal and to follow the VCV Rack voltage convention, we have to multiply the output by 5. Basically, audio range goes between -5 and +5, and since audio signal generally goes from -1 to 1, just it means you have to multiply by 5. The right channel has a sawtooth signal multiplied by a gain and a gate here, which will allow to make the signal. Yeah, I guess you hear this. Here I can switch with the gate, which is basically a button. And I can maybe try to highlight using the hash paragraph. Also, maybe I have to, I am going to copy paste, it will be faster. And it's recompiled. And now when I hit the button, it's also colored by this red, which is quite nice. And as you see, as soon as I change, save, it's recompiling instantly. It's quite fast with the interpreter backend. And okay, this is the first example of code that we can have. A second, more complex, using CV input. Maybe I will directly, yes, switch to the third one, which is basically this VCO.dsp, which is basically a standard example of the VCV prototype that exists in JavaScript in Lua and that has been ported in Faust. So I think I can load it directly from here because it's part of the standard example. I can edit. So now I have this code, and so if we try to understand what it's doing, basically it's outputting a sinus, which is produced by multiplying a phasor, and this phasor is going to be has a frequencies which is going to be the addition of two signals, something which is produced by a knob slider, so the first knobs here, and also a CV control, which will be the first CV input, which is going to be converted to a frequency value following this 1 volt per octave convention. So if I connect this, and if I connect like this signal here, yeah, so you see that the pitch is controlled at the same time as this button, but also with this sinus signal which is added, so you make this nice combination of the button and the control signal. Okay. And I am going also to demonstrate a MIDI controllable organ like DSP, which is also now part of the example. I can load it. It's an organ DSP. I have to edit it. And so, well, it's basically an organ done using additive synthesis. So for a given voice, you have the addition of 3 partials. You have a panner, you have an ADSR envelope with some fixed value that is going to be used. And you have here, you see that the process basically will be connected to 3 inputs: the pitch, the gate, the valve inputs. In this case, we want to use a VCV CV inputs, which are going to control the frequency, the gate, and the velocity of the note. And then here, to convert between the pitch, which is going to follow this 1 volt by octave convention, we use this. Okay. Okay. Jan told me that I have to stop talking when I'm doing sound and control. Yes, so now I am going to connect. Here I have this MIDI CV input. I have to connect voltage, frequency, gate, velocity on the 3 different control voltage input, and assuming I have my keyboard here. Do I need to check the MIDI? Yeah, it's supposed to be. It's supposed to play something, but it doesn't play. Why? Yes. I see that it's playing, but I don't hear any sound. Yes, maybe you hear something. Do you hear something? Yeah, okay. So it's basically a monophonic. So it's a monophonic MIDI synthesizer, so you only have 1 voice. But you have this MIDI 1 voltage convention CV input running. And yes, maybe I forgot to say that in VCV prototype, you can only describe monophonic instrument or effect because, well, it's done like that. And doing polyphony at the VCV Rack level, at the programming level, is a bit more complex. So they decided not to do that into this programmable module, and it explains also that you cannot do more than this simple organ. Going back to my page. Yes, maybe I can show you something a bit more demanding. CPU at the CPU level, like this physical model that has been initially designed and programmed by Romain. And so it's a model of a bell. And here also I have done some connection of some part of the GUI. The gate of the bell to hit the bell is connected to the switch 1 button. You have knobs that is connected to the gain, and then this bell is connected to a free verb, and the free verb also has some knobs that are connected to the VCV prototype UI. So if I hit the button here, I have, and here I also describe the fact that yes, the button becomes red when it's hit. And if you look at the CPU meter, so you see it takes a bit of CPU because, well, it's in interpreter mode, but while you have a physical model running into a free verb, and it's running in real time, sample by sample. It takes a bit of CPU, but it's usable. Okay. Next section concern this VCV, this Faust to VCV Rack tool. So you probably know Faust to something tools that we have developed over the years, like Faust to VST, Faust to iOS, Faust to Android. So that basically allows to transform a given DSP program into a binary, a plugin, an application, depending of the target. So it's a work in progress, as you will see in a few minutes, but you can already use it to describe a monophonic or polyphonic instrument, and you can also use a sound file if you need to. And we have installed everything into the Faust IDE so that you can export ready to compile folder from a given DSP so that you can finish compilation on your own machine and then install the resulting program into VCV Rack. In this development, we have done some alternative choice concerning this range adaptation. So in this case, the architecture choose to automatically do some conversion for you, so you don't have to multiply the output by 5 anymore. It's done by the C++ architecture file. Same for CV control. And we also, for the polyphonic case, we follow the Freck gain convention that you may know if you already developed with Faust. It's a way to describe a polyphonic aware, MIDI aware, and possibly polyphonic aware instrument by mapping the frequencies, the gate, and the gain coming typically from MIDI keyboards. In this case, since we are into this VCV model, we are going to automatically map the MIDI value with 1 volt by octave convention to the frequency which is expected on Faust DSP side. And you are going to use this envoice none parameter if you use Faust to VCV Rack in a terminal to choose a number of voice you want, up to 16 voice since it's limited in VCV. And if you want to choose between, first, this Faust to VCV Rack tool is going to create the GUI for you. So it will, as usual, analyze the DSP code and find out slider, button, switch, bar graph, and it is going to create a GUI. You will see that it's still a work in progress because you see the GUI is not so nice for now, but basically the idea is that the number of button and any kind of user interface item is going to be created automatically for you by the Faust to VCV Rack tool. But if you want at some point to have a given control be connected to a CV input and not to a regular knobs. You can use this CV and metadata to connect to a given number of, well, the first or the second or the third, the index of the input you want to connect to your parameter. So if we take some code example, here you see that we have the Faust to VCV Rack version of the first code we were looking at before. So this is this example with two different signal on left and right channel with the gain and gate button here and check button to hit to make the sound work. And here in this case I can directly use the Faust IDE. So here it's supposed to, and I'm going to change a bit this so that we can edit the name of the code. I can possibly test it into Faust IDE, and then I can export it. I have a new VCV Rack platform and I have 3 different targets. You see that there is still a typo here. It ends by soul, but it's not to be related to soul at any. It's not related to soul, but it's a typo. And here I'm going to choose VCV Rack, which is basically a monophonic target. I hit compile. I download the result. I have to close VCV Rack. Each time you want to add a new module into VCV Rack, you have to load it again so that it detects the module. So here I am going into my download folder. I have this binary folder. I can go into PAW1. PAW1 actually contains again the source code and the makefile, and you do make install. It compiles everything. It does install the resulting library into VCV Rack. You open VCV Rack, and now you see a new Faust module. So you see this basic default GUI, that you know it's PAW1, and you can connect it, make it work, connect it, and it's supposed to work. You have the gate button. Okay, so basically it behaves like the VCV prototype version, but now you have the specific GUI which is generated for you with 2 buttons and 2 knobs. Yes, this is the first example. Sorry. Just to close my. Yes. So the second example I'm going to show is a bit more complex one with polyphony. Polyphony, it's here. So it's, well, again, similar to the organ version we had just before, but now we are going to generate a real polyphonic instrument. So again, doing that using the Faust IDE. I think I have to do that to change again the name. So I can execute it. It's some additive synth with a master control, a panoramic, and 3 partial that you can control. Exporting it. Here I'm exporting to polyphonic 16 DSP. Yes, I have to go there. I have to close. I have to uncompress. Second example. Compile it. Up. Install it in VCV Rack. We'll remove this one, so I have this second one, so with a difference in user interface. I can connect this 3 control voltage inputs, and here I am supposed to use a real polyphonic mode, so I have to select here polyphonic 16 channels. So basically it means that each note we use in alternatively given cable into this 16 MIDI cable, and maybe I have to yes, because my velocity working, and I can connect maybe this. It's a 16 polyphonic instrument. And to finish the last example, if you want to connect this polyphonic instrument into an effect, then you have to compile a polyphonic effect, which can be done. Again, changing the name. So 3, compiling it, so it's a free verb, exporting it, 16 channel, compiling it, download, closing the VCV Rack, compiling and installing the new module, reopening VCV again, installing this polyphonic reverb, connect my polyphonic cables here, and again. So as you see, it's still a work in progress. We have to improve the automatic GUI generation. We have to design a more beautiful layout and probably choose more beautiful buttons, and well, we have to design some specific widget, I guess. So this has to be known in this case completely using C++ code, because you cannot prepare the template, SVG template. So I think, well, I think it's more or less time to to finish the demo. I hope you were able to understand something and to hear something. And I can try to answer the question if you have some.
Thank you very much, Stéphane. It was an impressive demo because you did everything live,
Yes.
and it went quite well. So
yes, it's always a bit.
We had a little bit before that to restart the Faust service, and but that was okay. And so maybe there are questions.
Yes. About yes, I asked some question about the SDK. Yes, the SDK is completely separated from the application. One question is about how you produce the module. Well, in this case, we are getting the source of the module, and the source of the module is supposed to be obviously, you have to compile it for OS 6, Linux, and Windows each by each, but the make file is supposed to be cross-platform. I've never tried right now. I only tried on OS 6, but the way the VCV Rack SDK is designed is that you are supposed to generate the binary for each platform you want to use. Yes. But you have to do it yourself. We may be able to produce some binary directly from the Faust compiler at some point, but it will take a bit more time to install everything on server side to be able to produce ready-to-use binaries. Yeah.
What is the difference of speed between the interpreted mode and the really compiled mode?
I guess it depends of the DSP. I would say between 3 and 15.
Okay.
Probably, yes. Yeah, it can be quite slow, but well, it's the nice thing is that compared to JavaScript or Lua, which are also interpreted language available into this VCV prototype, it's comparable or even faster in some case. So since the point of this module is basically to prototype things, I think it's quite okay to use this interpreter. And again, it's much easier to deploy. This was the initial reason to use it instead of the LLVM. Okay.
Yeah, but we could imagine to have the LLVM version
yes.
also.
Obviously, I did the LLVM version. Right now, it's, yeah, I can show you. Right now, it's defined into the code. Here I have, this is the code of this prototype. And here, you can see that, yes, I have the both version. The DSP factory is the LLVM version, and this is the interpreter version. So you can possibly, if you are a developer, you can move from the LLVM to interpreter version just by defining this compile type flag. See, right now I don't like that, but obviously it works also with LLVM. I've already tried. Yes.
So the problem would be that
Stéphane, is so you have the LLVM version also working?
Yes, at least on OS 6, yes.
That's great. The only gotcha there is that you have to be sure if you're running something in Rack that the LLVM versions don't collide. So
I had some discussion with Andrew, and I think he wants to have something not too complex to deploy.
Yes, I remember that. Yeah.
And he's already fighting to deploy a pure data engine for the pure data version.
Right.
So I guess if we can use the interpreter version for the regular version, it will be okay, probably for most users. And if more demanding user want to compile the LLVM version, why not? Yeah.
Is that in the repository of VCV Rack, of VCV prototype, or?
Yes, it's a branch. It's a Faust branch into VCV prototype. So Andrew recently moved my pull request as a branch. So you have to switch to the Faust branch and you can try it. Yes.
Mm-hmm.
But Stefan, we could also release this prototype module, a specific version of the prototype module that based on the LLVM version, without having it being part of the VCV Rack, right?
I don't know exactly the status of. Well, it's
maybe it's not open source. You mean?
Yes, it's open source. Obviously, the VCV prototype it's on GitHub, but I'm not sure we can decide to have our own version of the prototype, the binary version of the prototype. I think the right way will be to be merged into the official version of this module, and so that it will be accessible for everybody, and even in Windows and in Linux, which will be quite well. This is the goal at the end, to have a binary version of this module available for the 3 platforms.
Yeah, but no one keeps you from distributing binaries for which you have the source code up.
Yes,
I mean, that's perfectly okay, and I know that my students would need some binaries to download if they want to use that.
Yeah. Okay, maybe
that would be if you just put it somewhere on the Faust website, or maybe. Right.
Okay.
Oh, there is an interesting question by Florian on the.
Yes. Maybe I'm not sure about what you mean by mixing audio port and CV port. Right now, what we can do at first level is decide if we want some parameters which are usually control write parameter in Faust. In this model, we can decide to associate them with CV metadata. In this case, they become CV input. But they are not CV input at the same time as GUI elements. You have to choose one of the 2 possibilities. I'm not sure it correctly answers to your question, but maybe we can discuss that again. Well, to be honest, I'm quite new into this VCV model, and I will be happy to have feedback from more advanced user of this model, and possibly the choice we made about this automatic mapping of CV values and range issue, and maybe we can have some help from more advanced user to see if we have to make the model more general or add some compilation option to choose between different models. It could be interesting to follow the discussion. Yes.